Okay, tonight is the 30th of October, and we have only the faithful with us tonight. We're going to talk about any remaining questions for the exam, etc. There isn't any set format for tonight. There isn't any planned discussion. This is completely open. So the first question out of the box was explain the Gaver-Stehfest algorithm, and I think the easiest way to do that is to, of course, have you read the paper, which is what I did, but is also to explain that there's been an attempt over the years of having some sort of a sampling function where you would sample values of the Laplace transform function and then somehow create an inversion based on those samples. There was some work by Widder, which I'm noting here. This is some older work back in the 40s. And Widder talked about the idea of differentiating the function in the Laplace domain an infinite number of times. And of course, that's not possible, but each differentiation would yield another expression by which you could build an approximating function. And in a way, the Gaver algorithm has the same structure. That was the way that Gaver explained it, but it's not the same as the Widder algorithm. The Widder algorithm wasn't very good, to be honest. There was also a whole bunch of work done sort of in the 40s and 50s using Laguerre polynomials. This is not one of them. Those results are given in the notes, which are not included here. They're on the website, of course, but what I'm getting at is this is an approximation for the Laplace transform, and you could use a sampling approach for this one where you would take the weights and abscissas, which are known, they're in any given numerical analysis text, and you would sample the function f of s, and then you would utilize this. You could see you'd have a system of equations, and you'd set that up in the form of probably a polynomial, and you could resolve the f of t values from that. Now this is a little bit odd because of the way it would work, and it turns out that there were algorithms based on Gauss-Lagueree quadrature for numerical inversion. They didn't work out very well either, and again, those are in the notes if you want to see. I went through a phase of my life when I was convinced that I had been gifted by God and could develop some new and unusual inversion algorithm. So I went back and I read all the old stuff and I rederived all the old stuff. The interesting one, as mentioned by the student requesting this, is the so-called Gaver formula. And the way this works is it's a sampling function, and depending on your ability to sample the Laplace transform, and the Laplace transform is given here. This is the f of s function, and of course s is the natural log of 2 over t multiplied by n plus k, and there's a summation. There's nothing wrong with this formulation, except in order to be correct, you have to take an infinite number of terms. N has to approach infinity. And what happens here is, you know, after years of studying this, and admittedly it's very hard to derive, I've only gotten close a couple of times. I remember another faculty member tried to derive it, and there's, you know, you have to have a background in statistical theory, and it is a queuing problem. That was a question that was asked. Gaver worked for Bell Labs, so he was focused on how to queue telephone calls, and this was part of their study. Well, the outcome of that is this algorithm for approximately inverting Laplace transforms. Where's the problem in this equation? You know, I know I don't usually teach you guys how to look for a problem, but tonight I'm gonna give you the option of looking for the problem. Who's not eating? Kajang, you're not eating. So the problem is the factorials? No. That's part of the problem. What's the problem? You want to throw a lifeline? Throw it to Mr. Ravi Kumar. Mr. Ravi Kumar, what's the problem with this equation? Perfect. Absolutely perfect. The negative sign causes this series to be divergent. So if you had perfect numerical sense, it would converge. But you end up with smaller and smaller terms being added, actually I guess larger arguments, but at any rate, it fails. You end up with larger arguments divided by larger arguments, which creates numerical instability. Even if you could carry it to infinite precision, it would still probably fail. So your immediate, you got it. It's the minus sign. So what that means is you're only going to have a certain number of samples before this thing starts to fail. And I think probably Alex showed you this, but let me zip down to it. And sorry for the skipping, those of you in distance learning land. This is an example of the Gaver algorithm, okay? And so when you start at 1, your answer's not too hot. 2, it gets a little better. 3, it gets a little better. 4, it gets a little better, and so on. Until finally out here at about 17, what happens, Gabe? What happens? Why does it do that? Why? Because of exactly what I told you. The numerator, denominator arguments get larger and larger. And you can see what happens is that it's converging and then kaboom. And of course it just goes absolutely crazy. Well, this was double precision calculation here. And this again is 25 years ago. I got it. But you know, computers haven't changed that much. Even the accuracy of microcomputers hasn't changed that much. What has happened is you have MATLAB and Mathematica coming on the scene. Mathematica claims to be precisionless calculations, but it has limitations too. It cannot realistically consistently go beyond machine precision. So there has to be something, it has to do some sort of trickery to do this. You're not going to fix this problem. That's my point. This one is done. So if I told you the right answer is this dashed line, and somehow you're supposed to figure out an extrapolation formula to get to that dashed line, what would you do? I actually had several people try to solve this. You know, let's just say you accept Gaver's algorithm as correct, and now you want to create an extrapolation formula for it. Now, can Gaver's algorithm be improved? Can it be changed? Read the paper. There are other formulations for it, but essentially it only has one form. It's this. No matter how you formulate it mathematically, it's going to be divergent, okay? So what do? Do you say that n cannot be greater than 17? Or n cannot be greater than 16 and accept that? Now, how would you make an extrapolation formula? Anybody? Mr. Desai? No, that won't work. Sorry, good guess. But I was thinking that instead of, you see, this plot doesn't really make sense because the values are still converging. But what if we plotted 1 over n and we plotted the function here? Then it would tend, as n went to infinity, this would tend to 0. And this is exactly what Gaver proposed. Okay? Gabe, that's okay. Then you fit that with something and you extrapolate to 1 over infinity or 0, and there's your answer. Great idea, right? It didn't work very well. It didn't work very well. And just like the story that I told you about the engineer and the guillotine, so Gaver came up with this beautiful guillotine, but it didn't work very well. And then Stehfest came along and he said, well, there's a better way to do this. And what he did is he showed how to make an extrapolation formula. And I know this really looks god-awful, but it's relatively simple in concept. It's a collocation polynomial. What's a collocation polynomial? Whatever points you specify, the polynomial goes through all of them. And so you can extrapolate this collocation polynomial back to its 0th point or its infinite point, however you want to formulate it. So that's what the Stehfest algorithm does. Now, remember the rule, the more complicated something is, the easier it is to break it. So if the Gaver algorithm is only good to 16 terms in double precision, can you go to more terms than that with the Stehfest algorithm? No. Okay, so end of discussion. Now, if you take Dr. Valco's class, and I encourage all of my people to do that, he's going to talk to you about other variants of the Gaver-Stehfest algorithm. He's going to blow your brain clean out of your skull because he spent the last 15 years of his life playing with this problem in Mathematica. And he and a bunch of other numerical scientists have all come up with their own formulation of an advanced version of the Gaver-Stehfest algorithm. It goes under different classification names. He uses Mathematica. In theory, you could use Mathematica. Let's say you wanted 100 decimal places of accuracy. You could drive this thing to continue calculating until it gets there. Number one, it's going to be extremely expensive computationally. And number two, there's no guarantee it's going to converge. Just FYI. Okay? So some of the things that you see in here that I've shown you have actually been generated in Mathematica using that algorithm. Probably not so much in here, but some of my student work, because I trust the algorithms that Valco's developed in Mathematica for that purpose, and they seem to be fine. That's the end of the discussion about the Gaver algorithm. The Gaver algorithm itself is, I'm not expecting you to derive it. It'd be nice if you tried, and maybe somebody has some unique skill set that I don't, and they can show the class a nice short presentation and everything, but it's essentially just a sampling algorithm to generate the inverse Laplace transform. The algorithm itself is not sufficient. I know it looks ugly and everything, but you cannot take the arguments to infinity. Now, Mr. Desai, you implied that what you would like to do is take this series and make it convergent. Okay? Tell me how you would do that, and you don't have to do anything else in this course and you get an A. You prove that you can make that series convergent. No matter what the arguments, you get to go home a free man. Otherwise, I'm throwing you to the sharks. Any ideas? Cam? Cam's like, free. Let me put it this way. You will invest a lot more hours trying to solve that problem than you will everything else. And if it could be done, it would have been done. I know that's a terrible thing to say to young people, but I don't know how we would do it. I thought maybe we could remap it, you know, look at a general formulation that became a positive series instead of an alternating sign series, but I don't have it. I don't have the skills. So maybe one of you guys can. There may be some algebraic theory out there that would allow you to convert, you know, a binomial series like this, an alternating sign binomial series like this to something else, but I don't know. Yes, sir. It has to be the binomial coefficients, this thing. So as those arguments n and k get larger and larger, you know, it's a big number divided by a big number, and I think it's just natural that it's going to crush the calculation. It's a summation of that. Yeah.
I don't have a question, but I have some comment. When you said that n goes up, when you increase, even if you increase precision to infinite precision, and you increase n, you're just pushing the n where it starts diverging further away. It doesn't stop.
In a manner of speaking, that's true. But there are alternate formulations. And again, you know, take Dr. Valco's class. He's in love with this problem. Maybe he has some advice for you. But nothing is free. When this algorithm came out, it changed the world, for us anyway, because it allowed us to directly compute the inverse Laplace transform without having to use complex arithmetic. And that was a big, big thing. So all software, you know, that does well-test analysis, etc., it uses this algorithm and approach. They will never tell you what the Stehfest coefficient is, but I bet it's 16. It might be 18 or 20 in some sort of a hyper, you know, precision format, but I bet it's 16. And the other thing, well, I just forgot what I was going to say, but it was about how it's formulated. You know, they're probably just calculating in a simplistic form. I did give you the table of coefficients for all of this, and if you want to use that, you could program it in Excel or something like that. We tend to be lazy, So we calculate the coefficients every time. It's trivial to do that. There's not much loss of computer time, but in theory, you could just store the coefficients. Okay. Next question. Okay.
I have a related question. So on Dr. Valco's website, he's listed like 1,500 works where people have their own
Algorithm.
algorithms. So is it that we keep using the Stehfest algorithm in this form in petroleum engineering because of inertia, or is there really no other alternative for our problem?
There's plenty of other alternatives. Yeah, I would roughly say that some of those are going to be extremely difficult to implement in simple languages. I would defer you to him. You know, I did give you those two papers in the reading that were about algorithms, you know, historical reviews of algorithms. But you're right. Those were done in the 70s and 80s, and I imagine the proliferation is extremely large. There are various families of inversion algorithms that work on complex arithmetic. Those are going to be one class. I'm sure there's several hundred of those. There's going to be some that are sampling functions. There are others going to be based on Laguerre polynomials or Laguerre quadrature. They're all going to have some weakness. I don't know what that weakness is for every one, but I do know that if you push hard enough, you're going to find a weakness. One of the things that you can tell that whenever you're looking at results in a computer program is whenever there are irregularities in the calculation, like there'll be a bounce or that sort of thing, that's generally where functions have been spliced together and they're non-differentiable at the splice. So just be aware of things like that. I know that's not exactly answering your question, but unless everything is continuous, you're liable to pick up some damage or some amplification of error in that. Honestly, I think the simplest answer is momentum, but I think a more accurate answer is like the Bourdais algorithm for the derivative. It's not always right, but it's always consistent because it's the simplest algorithm that really generates a pattern that is consistent. This, are you asking me, does it generate 2 and 3 decimals of precision? Yeah. Does it always generate 2 or 3 decimals of precision? It's hard to say. The version that I gave you in Excel, for certain problems, it'll give you 6 or 8 decimals of precision, but certain problems, it's going to give you 1 or 2. There's another thing that I thought about. Some problems that have jump discontinuities, the Laplace transform is valid for those, but it doesn't like them. And so there's probably algorithms that process jump discontinuities better than others. Because I know the Stehfest algorithm does not like jump discontinuities. It's a sampling function, so it'll probably miss the jump. That I was thinking about that whenever I spoke before. Okay. Other questions? Thoughts? The one thing I regret about this particular term is I don't actually have you making calculations with this algorithm. So, sorry. I think maybe you might have to for the final. Let me see. I don't remember exactly precisely what I put in the final. No, I needed to shrink it. Sorry. Yeah, this is the right version. Okay, nope. No, the first problem 1 is analytical. Problem 2 is analytical. Problem 3 is analytical. Problem 4 is analytical and a pain in the ass. And problem 5 is analytical and not. No, I don't require you to use it for any of these. You could for the bonus. Yes, Gabe. I don't see. No, I don't believe. I believe they're all analytic problems. Number 1, is probably not solvable. It might be if you resort to method of residues, just as a comment, but it won't be solvable in the methods that I've taught you here. But it might be solvable in method of residues. There is a jump in the Gauss-Lagueree solution where they go from here's the form we're looking for and here's the result. So good luck with that. You know, it was always simply put, here's the answer or something like that. The second one should be okay. I actually gave exam problem number 2 to somebody as a PhD prelim problem, and I didn't think they were very, what's the right way to put this? The word I'm looking for is not smart, but very well motivated, but they did a nice job on it. I was impressed, and you know, it's not a hard problem, but the algebra is ugly, so be aware. And again, I'm not saying that you can't use a product to check your work, but you're going to have to show all your work. Problem 12.24 is very straightforward. And problem 4 is, I don't know, do with it what you want. I made the mistake of trying to prove that the rectangular hyperbola was valid. You know, I'm like American and you're like French. You know, you assume it doesn't work. I assume that it did work. So I worked that huge derivation. I did all my algebra was to come up with a form that agreed with their concept. But I'm just going to say it probably is not correct. So to assume that that simplification is correct. If you stare at the rectangular hyperbola long enough, what does it look like? Not Horner. Who's the other guy that did build up equations? Before them? Yes. So what does the term C over B plus T look like? It looks like a single term expansion for an exponential, right? So it is an approximation of Muscat's equation if you want to think about it that way. So where we're at right now is the key would be to prove that that equation, or that part of the equation, the C divided by B plus T, is essentially E to the minus alpha T. If you could do that, that might, well, it's impossible, right? I mean, I think I just gave it away, but I really like the discussions that people gave to this paper, and I really like their responses. It was like, no, we're right. No, you're wrong. No, we're right. No, you're wrong. You'll enjoy reading those, I'm sure. You decide. This is Fox News. We report. You decide. Cam, don't say fair and balanced. Let Gabe say it. Yeah. Thank you, Mr. Ravi Kumar. The last problem is very straightforward. I told you how to solve it. So.
Mr. Liu is not here, but there was a class when he asked you about the radius investigation. Well, there's a statement in Dragon's book where he says it's, radius investigation is essentially infinite because it's like diffusion. You say you'll get back to us.
Okay, so Raghavan is actually the one that motivated problem 5. Because when I was a postdoc, I took his classes, and he showed how to derive the probe radius formula, which is A, and then I took B and developed a problem out of that. I wanted to prove that you could use the probe radius formula and also derive an expression for the radius investigation that was not based on a simple extrapolation. And it turns out that that would be the peak of the second derivative. If you look at the exponential integral solution, you're right. It doesn't have, it can't be solved. You have to pick a point. And one of the things that you could do is you could pick a point. Well, that's why 5.2, you take second derivative, it gives you the maximum. Well, you'll have to figure that out. But solving equation 5.2 equal to 0 doesn't work. And that's what you were saying, is that it's infinity. But let's say you decided to solve it for 1% of pi, whatever that is, then it can be solved as a root problem, as an example. Again, I know I'm saying this into a microphone and it's being recorded. I don't care about the radius investigation. It's just a concept of how far something propagated. And if you want to consider a finite speed of propagation, you're going to have to decide what your, how do you say, your basis is, you know. And if it's the probe radius formula, then it would be a linear extrapolation of that. If it's some other criteria, if it's a second derivative criteria, that's fine. If it's the first derivative of the instantaneous solution, that's fine. Whatever you decide. It's ironic that all of these tend to a square root of diffusivity times time. So that was a kind of a surprise. In other words, the only difference in all these equations is what? The coefficient out front. So they're all propagating at square root of time speed, if you want to think about it that way. Okay. I'll go over this one more time because I've had a couple of questions on it, and I know the people in this room asked them, or at least one of them did. On problem 6.7, this is straight out of the notes. 6.8 and 6.9 are not in the notes. Have you already done these? It's straightforward, right? There's a very straightforward way of doing this. No problem. Okay. You assume the constant pressure case, solve it for that. You assume the linear pressure case and solve it for that. Not linear reservoir, but pressure as a function of time. P is equal to some constant A minus some constant B times time. So the pressure is declining with time. Everybody got that? Good. Yes, sir. Yeah. Did I not put the bonus in here? Okay. I don't think I have it here. I have to go to the website. Okay. Mm-hmm. I think what I would prefer is that you'd send me a note saying you're going to do that, and then tell me what you're going to do. Give me 3 or 4 bullet points, and then ask me for a reference or something. I'm happy with that. I'm okay with you just asking me, but if you say water influx, there's 1,000 papers, and that's probably not an exaggeration on water influx. So I might just be lazy and say, okay, derive the Carter-Tracy method for water influx, which is actually really easy. But, you know, something like that. And I don't mean it's really easy like a child could do it, but after having this class, you should be able to do the Carter-Tracy water influx problem. I would prefer that you tell me you're going to work on something so I, A, have a record of it, and B, that I either, and you're welcome to send me a paper and say I want to rederive equation 17. But if equation 17 is something we've already done in class, forget it. You know, just as a comment. How's that? Is that enough? Okay. And by the way, you're not limited to these subjects. You can. I did have a couple of people maybe 5 years ago that tried to derive their own inversion algorithm, and I'm sorry, I had more than a couple, but a couple of people actually came up with something really clever. But you can't expect on a final exam to compete with the 1,500 people who've devoted their life to inverting the Laplace transform, unless you're brilliant or extremely lucky, and that does happen every now and then. Which I'm certainly happy to encourage. If you guys want to try something different, I'm certainly happy to encourage that.
What was the topic that got a 10?
Sorry?
What was the topic that got a 10?
That was it. The Laplace transform. Yeah. The young lady that worked on it, it wasn't perfect. But what I like is concept, then develops the methodology and then demonstrates the methodology. And she did a really nice job. Now, if I tell you that it was a friend of Stehfest, that would be true, or a friend of Gaver, that would be true. But it was just that she had a really novel approach to it. Probably not unique, probably easy to break, but just clearly, you can tell sometimes by volume and by looking at someone's thought process. You the guys are the only ones here, and the people on the camera can see me, but, I like my students to circle the problem. Hopefully they've got the whole thing circled, and then slowly spiral in on a solution. I jokingly call it the firing all your cannons in all directions at all times. This is how my daughter solves problems. She just guesses until, it's like throwing darts at a dartboard until she gets close and somebody tells her you're close. The real world doesn't work that way. You have to circle the problem and then slowly constrict yourself around it. And there is often at times a case where you're working on the wrong problem. That's life. Hopefully in the afterlife, maybe they turn the heat down a few degrees or something for those of us who've worked really hard on things that didn't matter. But I don't know. Just give it your best shot. I mean, imagine yourself stranded on a desert island with enough food and water to survive, and you're going to go insane if you don't figure something out. So, maybe make your own alphabet or make your own language, or, come up with a way to communicate with coconuts or something, but treat that like this. Give yourself, you've got 40 days before this is due. Give yourself, I don't know, somewhere in those 40 days, give yourself a couple of days just to think about it. And, if you do your best to impress me, I'm sure I'll give you some credit. But just writing down, I thought about this and couldn't come up with anything, you can see the big X on your page. And, next time don't submit if you can't think of anything. What'd your parents always tell you? If you can't say something nice, don't say anything. If you can't think of something good, don't submit it. I'm not expecting very many people to do the bonus, but if you do it right. What else? Cam? You wish you were in another place, another time? Did you say I hit the nail in your head? This course has never caused anybody any irreparable harm. Sorry, I'm too far away from you.
Yeah, I just wondering what we should do in the step by step or the main steps.
Okay, for which problem?
For,
For the homework?
Yeah.
You got to show everything.
Show everything.
Yeah. Did I not mention that? For the homework, you have to show all steps. Did I not mention that? Yeah. That sounds like a big no-no on my part. Yeah, no details should be omitted here. Yep, there you go. I've done this a long time. Yes, sir.
So problem 2.1.
Yep.
So there's a weird issue with that. Yeah, so the question's wrong in the sense that they give you x squared plus x squared minus 0.9x minus 8.5 is the equation that you're to find the root for. And they say the root's between 2 and 3, but there is no root between 2 and 3. But the interesting thing is, if you change the minus 0.9 to plus 0.9x, you get the root between 2 and 3, but it's exactly at 2.5. So if you do bisection, you get it in one shot. So what I did was I changed the constant to minus 8.5 or something, so that I could demonstrate that I can bisect it 20 times. Is that okay?
Of course.
Okay.
Yeah, I never told you about my consulting job in Saudi Arabia. So I had something like that. I told the guy that their data was wrong, and he looks at me and goes, "You're the consultant, you fix it." And so I said, "Are you telling me that you want me to adjust this problem so it gives you the answer you want?" And he goes, "You're the consultant, you fix it." And then he left. And so, "You're the consultant, you fix it." And if anybody's offended by that, I apologize, but we did eventually work out a way to solve that problem without cheating. Saudi Aramco is the only company in the world that takes a flowing bottom hole measurement twice a year. They had a crew that went around and took those, and that data was magnificent, so I was able to get around it. But yeah, the consultant fixed it. But you're the consultant, you fix it. Sorry about that. I did not know there was an error in the book. So, oops. At least I know you're working.
You'll know for sure when I submit it.
Yeah, whenever it looks like it's written in crayon. Please do not do that, class. There are some people that's handwriting is absolutely atrocious. And yeah, I know. And I mean, it's not the right time to find out that we can't read your work when you submit it. If you have a question, contact Alex and ask him to go over your work. Please, I beg of you, do this. Even send him a scan sheet or something. Yes, sir. You know, I say use line paper, mostly because, and a pencil, mostly because people don't use either. And they go off the page, they write on the back, they do all this crazy stuff. I would prefer line paper, please. You know, if you don't have some, I'll find some for you. But I would recommend typing it, but that's your prerogative. Typing is going to take a while. Yes, sir.
I have a weird question.
No, I'm not attracted. What?
So, I was writing my solutions in LaTeX. So, do you want it strictly in Times New Roman font?
I don't care. If it's in LaTeX, that's fine.
All right.
But if it's in Word, I would prefer it be in Times New Roman font, because that goofy new equation editor that they uses some math type thing, and it looks, I don't like it. Yeah. By the way, porosity, not that anybody cares, is a circle with a bar through it. It's not this squiggly thing that one of those things does for phi. So just, it's irrelevant. Sorry. Didn't mean to. You get people making up their own symbols too. What are you two laughing about? Oh, shit. I bet you would. Do not do that. I can already see you typing it in Halloween font or something like that. Do not do that.
60 pages on Halloween.
I can imagine that. Or what's the one where every other letter is alternating case? You know, do not do that. We will not be friends if you do that. I know some of you are thinking that'd be really funny. Do not do that. Okay. I would be absolutely impressed if you did that.
You just
I think I told you that I made Mr. Jose at Kappa hates type curves, so I made the solar system and put him in the middle with all these type curves surrounding him. It made him insane. Don't do that either. This is a class, damn you. Make sure it's an exam. All right. I'll be online most of the time. There will be some, I'm not so sure about my trip to Indonesia, but I'm pretty sure there'll be internet at some point. So, yeah, my former student is the department head at the program in Indonesia, and this was the only time that I could do this, so my apologies. But there's also an SBE meeting after it, so I figured kill two birds, one stone. And yes, the SBE meeting's in Brisbane, but you guys been to Brisbane? I don't really know that I've ever seen anybody do work there. It's probably the best, Brisbane, Australia. If you're listening, Brisbane, it's probably the best lifestyle place on the planet there. I said it. Except for when it rains and everything floods. But I will be back here on December the 3rd. But I will always be online intermittently in between there. So, my apologies. Alex will be here. And, just send something to both of us if you want us to take a look at it. Thanks for asking that question about the root problem. I did not know that. Actually, strictly speaking, I love that little book. It's very handy for things. It's kind of old school, the Hornbeck book. But what else, guys? Everybody gotten good sleep, feeling good? No? What's wrong? Cam, with that haircut, you kind of look like Bart Simpson. Yeah.
Here's how to get jaundice now.
Thank you, Lisa. So you're saying you're not sleeping?
I mean, I'm sleeping like,
What are you dreaming about?
I don't know.
Equations?
Sometimes I had a dream, like, I don't know if it was last night or 2 nights ago, that we were under alien invasion.
Was I the the leader?
No, I don't think you made it dreams.
I didn't make it into your dream.
No, you didn't make it.
Yeah, well, just think Christmas morning when you wake up screaming because you forgot to turn in your 620 exam. Are you okay?
I suddenly got a cold sweat thinking that the paper would be due this month, next month. I think my bullshit. I mean,
When I wasn't in school, for like the last year when I wasn't in school, I would have dreams that I forgot to turn, that I was in school and I forgot to turn something, I forgot to submit something like a month ago, or I'm like, oh, the semester's almost over and I haven't submitted any work, what's going on?
Cam, how old are you?
24.
I'm 31 years older than you, and I still have that dream.
That's all my life is going to be now.
Yeah. Just wait till you start paying property taxes and income taxes, and you're like, I paid that. You're going to jail. Officer.
Maybe I need to start getting a little planner, a little notebook to,
What, that you can do in your sleep?
yeah, it'll keep my brain a little.
Mr. Desai, you okay, buddy? You don't ask a lot of questions. I worry about that. But you got a good heart, so we'll let it go. You're not like Mr. Ravi Kumar. Nothing. What are you going to do when you grow up? Oh my God. I can imagine 25 years from now, you sitting in this room, lecturing to yourself.
With a t-shirt on every day. New t-shirt.
Only a t-shirt by that time.
T-shirt's long enough.
But I'm a professor.